Welcome back to Module 4 of Working with EEG Data. And this lesson is about Fourier Transform. So this is what we already know. Before we try to interpret the signals picked up from EEG, we must pre-process the data. This can help us potentially remove artifacts. Some key questions that we're going to address is what is a Fourier transform and why is it important? How does convolution work? And what is discrete time Fourier transform and how is it useful? So we can take a bunch of sine waves and assign to each sine wave a different frequency, amplitude, and phase. So we can sum these sine waves together and then we can get a more complicated signal down here. But in real data analysis, we have exactly the opposite problem. We start with the more complicated, intricate signal, and we want to know which of the sine waves and which frequencies and which amplitudes and phases can we use to express this signal. The problem is significant for real EEG data, which has a lot of overlapping frequencies. So how can we tell what frequencies are present in the signal and with what strengths and with what timing? So fortunately, Fourier comes to the rescue, so yay. Fourier provided us an algorithm to decompose this sort of signal, and Fourier says that any signal can be expressed as a combination of different sine waves, each with its own frequency, amplitude, and phase. And one of the powerful things about Fourier transform is that it works perfectly for any signal, not only signals made up of pure sine waves. Any signal can be expressed as a combination of different sine waves, so we will be going through the Fourier transform and see how to decompose complex signals. So, Fourier transform is an incredible important signal processing technique in time series data analysis. It works by computing the dot product between the signal that you acquire from the EEG sensors and some waves of different frequency, which are the kernels. Remember that sine waves have three characteristics, which are frequency, power, and phase. And the result of Fourier transform is a 3D representation of the time series data in which the three dimensions are frequency, power, and phase. This representation contains all of the information in the time series data, which can be perfectly reconstructed from the result of its Fourier transform. So I'll start with a general conceptual idea of how Fourier transform works. So we start with a signal, and this is a single trial of EEG data. You can see that the voltage fluctuations go up and down over time. And then we take a sine wave of some particular frequency and we line it on top of the EEG data, and then we want to know how similar are these two time series. The Fourier transform uses a dot product to get the similarity, which we'll talk about in a sec. And you can simply just think about how much of this sine wave can you detect in the EEG data. And for now, we'll temporarily call that similarity. So the amount of similarity is plotted here, and it is plotted in a position corresponding to the frequency of the sine wave. So this is just one step getting from the time domain into the frequency domain. And now we just repeat this step for another sine wave with a different frequency. And another sine wave, again, for another frequency. And now you can see that we're constructing this full representation of the time domain signal in the frequency domain. So hopefully the mechanics of this will become more clear in the next few slides. Many techniques for extracting frequency information from a time domain signal rely on a mathematical procedure called convolution. So before learning about convolution, you need to become familiar with the dot product. And taking the dot product is simply the sum of the elements in one vector weighted by elements of another vector. And to compute it, you just need to multiply each element in one vector by the corresponding element in the other vector. Then you sum all of those points. So let's visualize what the dot product is about. Consider two element vectors. These vectors can be expressed as lines from the origin Imagine just drawing a line from the end of vector A, so this is the end of vector A, to vector U, such that they intersect at like a 90-degree angle. So the length of this projection onto the vector is the dot product. And several frequency and time frequency decomposition methods involve computing the mapping between two high-dimensional vectors, such as a sine wave at a particular frequency in a time series. So let's move on to convolution. Convolution in the time domain is an extension of the dot product in which the dot product is computed repeatedly over time. Convolution can also be performed over space, but for EEG analysis, convolution over time is used. So we have one vector that is considered the original signal or the original data. So in this example here, let's just say we have our signal, which is called the sawtooth signal, and another vector is considered the kernel. So and it can be like a sine wave or any response that you want. And the example here is this response. So this is the kernel. So imagine taking the kernel and flipping it backward and then dragging it forward in time so it passes over this signal. So as the kernel passes over the signal, it drags on the signal, and the result of the drag is something that is neither the signal nor the kernel, but looks a bit like both. So this is the result. And in this case, this at the bottom is the convolution of the sawtooth signal. We can see that convolution shows what features the signal and the kernel have in common. So this process of computing the dot product by multiplying each point in the kernel by each corresponding point in the data and summing all over the multiplications and then moving the kernel one step to the right continues. So that continues until the kernel has reached the end of the data. So the resulting vector is the time series of dot products between the kernel and the corresponding equal length windows of the signal. Convolution is often denoted using, convolution is denoted using the asterisk. So this equation deals with x convolved with h. And another way we can define convolution is just an integration of the multiplication of these two vectors, x and h, which is the kernel, so h is like the kernel, but you need to like drag it over the signal over time. So this is why we have t minus tau here. That basically is convolution, and this is a basic technique that we'll be using for extracting features from signals. Now let's make some waves. Sine waves can be represented mathematically by the following formula, where A is the amplitude of the sine wave, and F is the frequency of the signal, and T is just the time, and theta is the phase angle offset that you can see here. So the phase angle is a number that represents how many degrees a sine wave is out of phase with respect to our reference. So our reference can be 0 or another sine wave, and in this case, the phase angle here is represented how many degrees is like out of phase in this blue signal with respect to the red one. So now we can compute the discrete time Fourier transform. So the idea behind this is very simple. First, you need to create like a sine wave, and the original data here is in purple. So this is the original data, the one that looks like squares. And you need to approximate the original signal, which is the square wave in this example. So the first step corresponds to creating a sine wave and then computing the dot product between the sine wave and the time series data. So in this case, you will obtain a dot product between both signals, and then the process continues by creating another sine wave with a different frequency. So you just keep continuing this with like sine waves of different frequency. And so again, you will need to compute the dot product between both signals, and you will have a different response. So you continue by generating like more sine waves, and the number of sine waves you create is determined by the number of data points in the time series data. So you will obtain at each iteration a different forms of these sine waves, and you will try to approximate to the original signal. And my original signal in this example is just this, this square wave. Okay. So let me provide a general pseudocode that will perform a DFT of a random data for now. So let's begin with like n equals 10, which is the length of the sequence of the data. So the data corresponds to the set of random numbers from 1 to n. This is just an example of the data. And then we need to initialize Fourier coefficients, which will be an array filled out with like zeros of length data, and then the time array time starts at 0 to n minus 1 because 0 is included and divided by n, which normalizes to 1. And then you will need to create a for loop because you will try to generate sine waves at each iteration. Remember that the number of sine waves that you create is determined by the number of data points in the time series data. So so first you will need to create a sine wave. You can see the equation of the sine wave, the sine function, which looks a bit different because there's no sine function. Instead, there's an exponential and a minus I, so it makes a complex sine wave. You can also notice that the frequency of the sine wave is 1 less than the looping index f of I minus 1, whereas you might expect that to be defined by f of I, but the sine wave at each iteration corresponds to a frequency 1 step lower than the iteration. The first iteration of the loop produces a sine wave of 0 frequency, and this is called the DC component, which stands for direct current. And then you need to compute the dot product between the sine wave and the data. So the dot product computes the mapping between two vectors, so this will be the dot product between the sine wave and the data. So this is the general algorithm for computing the discrete time Fourier transform of the data. So the formula for the discrete time Fourier transform looks like this, and the discrete Fourier transform of variable x at frequency f is just the sum of the dot product between the sine wave and the data. So and n refers to the number of data points in vector x, and capital X of f is the Fourier coefficient of time series variable x at frequency f. So imagine that you have this time series. This is time series data, or time series signal, in which you acquire from sensors like brain signals or muscles or any electrical signal. And if you plot the data, you will get amplitude, which would be voltage with respect to time. So this will be vector x of k, and then if you compute the Fourier transform, you're creating a dot product between different signals at different frequencies. Then the result will give you a frequency domain response. So this here on the left is the time domain response, and after Fourier transform, this results to what's here on the right side, which is the frequency domain response. So you will obtain, after computing the Fourier transform, you will obtain power with respect to frequency. And you will see which frequencies have more power relative to other frequencies. So let's have a final example of this to wrap it up. So if you compute the Fourier transform of this signal, you will obtain something like this. So the Fourier transform of the signal, and you will see that you have more power here at 1 hertz, frequency 1 hertz, and the rest of the frequencies are around 0. So we could say that this signal corresponds to a 1 hertz signal. But when you compute Fourier transform in this second signal, you will obtain a higher frequency, so the signal looks like it corresponds to a 5 Hz signal. So this should be already familiar to you from the first section, which I briefly explained this. And then this third signal corresponds to the sum of the first and second signals. So if you sum up this, you will obtain a signal with different frequencies. And there we have it. You see that there's enough power at 5 Hz, but you will also obtain some less power, but greater than 0 at 1 Hz. It will tell you that the frequencies that characterizes the signal corresponds to these two frequencies. So this will give you an idea of how many frequencies you have in a signal. When you acquire a signal, you need to identify which frequencies you have. So with EEG data, you'll be getting noisy signal, and you need to describe how many frequencies you will have in that kind of signal. All right, so to summarize this long lesson, the Fourier transform is a powerful method to characterize a signal. The discrete Fourier transform involves splitting a signal into different frequencies, which can allow you to extract relevant information. And so what's next is motor imagery. I'll see you for the next lesson.